So, so in the videos we discussed mainly two things. One is simple linear regression. The other is multiple regression. So we can use Excel to do those regression analysis, and I think that this is the file we ended up with. We got the output. We use the Excel function to get the intercept and other coefficients for the variables. So we got those coefficients. None of them are 0, but we have more numbers here. We have standard error, t-stat, p-value, lower limit, upper limit. What do those numbers mean? So we will talk about those things in today's class. So those numbers are about statistical inference. So in the last lecture, we said for the population, if we talk about simple linear regression, the format is y is equal to beta 0 plus beta 1 times x. But when we do the regression using the sample data, the format is y hat is equal to b0 plus b1x. We are not using beta because the beta, that the first one is for the population, and we don't have the data for the whole population, so we use data. We use the sample data. From the sample data, the regression model has parameters of b0 and b1. So in the previous chapter, we learned how to use confidence interval or interval estimation or hypothesis testing to estimate the population parameters. So similar story here. So the true population parameters are beta 0, beta 1, and so on and so forth. But what we have is b1, b0, and so on and so forth. And we can use hypothesis testing or interval estimation to estimate the population parameter. So before that, we have to make sure that our regression analysis is valid. So how do we know our analysis or our regression model is valid? There are two conditions we have to satisfy, we have to check. So the first one is for any given combination of values of independent variables like x1, x2, x3, and so on and so forth, any of the combinations, we have to make sure the population of potential error term, the epsilon, is normally distributed with a mean of 0 and a constant variance. The mean has to be 0. The constant, we don't the variance, we don't have a specific requirement for the value, but we have to make sure the variance has to be constant throughout the whole x values. So that's the first one. The second one, the values of epsilon, the error term, has to be statistically independent. So those two conditions we have to meet in order to make our regression model valid. So how do we explain this in terms of the regression model? So in this figure, we have our regression model. We just use the simple linear regression model. We have x-axis and y-axis. We just put the whole picture down. So x and y, and we have a regression model. Here's the regression model. Y hat is equal to b0 plus b1x. So that's our model from the sample, and we draw the line here. In order to meet the requirement, we have to make sure that the actual y value, so we have different x value, for each of the x value, the actual y data has to be normally distributed with a mean on the line. So for example, when x is equal to 30, we have to make sure the actual y data's mean is on this line. Is equal to the corresponding estimated value, and the variance or standard deviation for all the x values has to be constant. So this large for x is equal to 30, and we have to have the same variance, same variance, same variance. So if we have a regression model and the data like this, our regression model is valid. But in real practice, it's really hard to put our data in this kind of format. I think we have show that it's really hard to do this. So in order to make sure the error term satisfies the two conditions, one thing we can do is to plot the relationship between the residual. So here the vertical axis is representing the residual, and the horizontal axis represents the estimated y value. So if we plot this relationship, we have to make sure the mean value has to be 0. The mean of the error has to be 0 for each of the estimated y value. And we don't have, and the variance has to be constant. It cannot be here the variance is this small and right there is this large. If that is the case, the model is not valid. So if the relationship is like this, very good, very good. Another thing we can do is to plot the relationship between x value and the residual. Still, for the residual, we have to make sure the mean is equal to 0. But here we have 4 figures, and let's see what problems we have here. So if we look at the first one is x against the residual. The mean is 0, but the problem is the variance is not constant. So for smaller x values, the variance is really small. So all the residuals are very close to the mean or 0. But when the x increases, the variance of the residual also increases. That is not good. That is not good. It doesn't satisfy our conditions. So if your regression model has this kind of plot for the relationship of x and residual, then the model is not valid. The second one, still x against the residual. So it's kind of curve. So when x is really small or the x is really large, the residuals are positive, and if x is somewhere around here, the residual is negative. That means when the x is small, our model overestimated or underestimated. When the x is small. When the x value is small, the residual is positive. So the residual is equal to the actual y data minus the estimated value. So if the residual is positive, that means our model underestimated. And if somewhere here, so that means our model overestimated. So that means our model is linear regression model, but actually the relationship could be nonlinear. So that's why when we use linear regression model to fit the data, this is how we get in terms of the error curve. And the third one, we have a lot of residual data that are a little bit under 0, and some data that is really far away from the 0. So if we have this kind of data, that means your data could be skewed. So left skewed or right skewed. So that's something we have to think about. And the last one is a plot for the relationship between the time t and the error term. If we look at this error term, the smaller one negative goes up, and goes back, goes up, and go back. So if there's a pattern, so that means the residuals are not independent. It depends on the previous value. It depends on the previous value. Increase, increase, increase. Then suddenly decrease and go back. So they are not independent. So if you see your plotting is like this for one of them, that means your model is not valid enough. So we have to make sure this is what we get. If you plot the relationship between x and error term or the y, estimated y and the error term. So otherwise, the model is not valid. Then if we plot the model we had in the last class, so this is what we have. So miles or the x value against the residual, this is one of the variables or one of the independent variables, and deliveries, that's another independent variable, and deliveries against the residuals. So the shapes are very good. So mean is 0, mean is 0, is the variance is constant, variance is constant. So we are good with our model. And in the output, we have this one, residual output. We can compare the predicate value and the actual observation and the residuals. And this is how we plot the relationship between the estimated value and residuals. So the shape is also good. Still, let's go back to the question we had at the beginning of class. So what are the t-stat, p-value, and the lower limit or an upper limit? So those are the results for interval estimation and hypothesis testing. So when we do the regression analysis, the first thing is to identify if there's any relationship between an independent variable and dependent variable. So if there's no relationship, the x does not affect y. In that case, the coefficient of x should be equal to 0. But that one is from our sample. So if we go back here, so here are the coefficients. B0, B1, and B2. So those numbers are positive numbers. So B0, B1, and B2. So we have all the values or all the coefficients positive. Does that mean the beta 0, beta 1, and beta 2 are non-zero? So here we have B0, B1, and B2. So all of them are greater than 0. But the population parameter are beta 0, beta 1, and beta 2. So those are just point estimators of those parameters. I lost one there. So having all those numbers positive, does that mean all those values are not zero? So in order to answer that question, we can do two things: interval estimation or confidence interval. The other is the hypothesis test. So if we do hypothesis testing, the configuration is, so in the null hypothesis, let's assume that beta j is equal to 0. There's no relationship between the x and the y. Or in other words, there's no relationship between the miles and the travel time. And the alternative hypothesis is it's not equal to 0. There is a relationship, or miles will contribute to the travel time. So this p-value is the corresponding result for the hypothesis testing. So in the previous chapter, we said if the p-value is small enough, we reject the null hypothesis. But if the p-value is large or is not small enough, we fail to reject the null hypothesis and we do not have the conclusion. So if we look at this one, the intercept, the constant term. The intercept, we can do this hypothesis testing. Say the null hypothesis b1 is equal to 0 and alternative is the b1 is not equal to 0. So the corresponding p-value is 0.5. So 0.5 is kind of a large p-value. So normally we select the alpha level or level of significance as 0.05. And obviously the alpha level is less than the p-value, or the p-value is greater than our alpha level. That means we cannot reject this null hypothesis. We don't have enough evidence to say that it's wrong, which means we do not have enough evidence to say this is correct. So although the B0 is 0.1, but we don't have enough evidence to say the beta 0 is not equal to 0. It could be 0, so we are not sure. But if we look at the rest of the two values, the second one is 3.5 times 10 to the power of negative 83, and those two values are really small p-values. That means those values, we can reject the null hypothesis. And similarly, we can do the constant interval. We have the lower limit and upper limit. If we look at the lower limit and upper limit, 0 is in this interval, so 0 could be a possible value. For the rest, we don't have 0 in the interval, so we can say, okay, 0 is kind of impossible. We can reject the null hypothesis that the parameter is equal to 0. So the t-test. So in the last chapter, we talked about the t-test, how to do the hypothesis testing and the constant interval. We are not going to spend time here. The constant interval confidence level. And addressing insignificant independent variable. So if we identify that one independent variable is not significant, that means there could be no relationship between that the independent variable and dependent variable. So how do we deal with that? So you have to look at the context. From your experience or from your practical experience, if the independent variable can be removed, or it doesn't have to be there, or it doesn't have a real impact on the dependent variable, you can just remove it. But you have to make sure practically you can remove it. But sometimes we have to get more information about the result. So one concept we want to discuss is multi-collinearity. So what does that term mean? That means there is correlation between your independent variable. That it could be x1 and x2. Those variables are dependent, or there's correlation between those two variables. So in that case, if you have a really large p-value for one of the variable, that means the the contribution or the impact of one variable has been represented by the other one, because there is correlation between those two. It doesn't mean the second variable does not contribute to the dependent variable. It's just that its contribution or its impact has been represented by the first variable. So in this case, you have to be careful. So if we look at one of the results, the intercept, mile, and gas consumption, so that's the result we have. So if you look at the p-value, if you look at the p-values for the two coefficients, one is for miles and the other one is for the gas consumption. For the miles, the p-value is really small. It's a really small one that we can say, okay, this independent variable has a relationship with the dependent variable. But if you look at the third one, the p-value is 0.658. It's a really large p-value. That means the coefficient of gas consumption could be 0 because we cannot reject this null hypothesis. Or if you look at the constant interval, the lower limit and the upper limit. So the lower limit is negative, the upper limit is positive. That means 0 could be a possible value for the population parameter. So in that case, if you look at, without looking at the name of the variable, just looking at the p-value or the constant interval, you may say, okay, the third variable does not contribute or does not impact the dependent variable, or the dependent variable or the trial time is not influenced by the gas consumption. But from our experience, there should be a relationship. So if we consume more gas, that means we traveled more. But why do we have this kind of result? That's because those two variables have a correlation. The miles you traveled and the gas consumption, they have a correlation. So from practical experience, if we travel more miles, we consume more gas. So of course, there will be a relationship. If we plot the data, so miles against gas consumption, so this is the plot we have. That's a very strong correlation. It's very strong correlation. The more miles we travel, the more gas we consume. So that's the story behind the data. It doesn't mean gas consumption does not contribute to the travel time. It's just the influence is represented by the miles we travel. So that's something we have to be careful of. So big data, we can skip that. We don't have to worry about that. Okay. So that was the statistical inference. Before that, we talked about simple linear regression. We talked about multiple regression, but there are more types of regression models. The next one we want to discuss is categorical independent variables. So we know there are two types of variables: quantitative variables and categorical variables. So far we have talked about how to model the quantitative variables. But in many cases, we have categorical variables. How do we incorporate categorical variables in our regression model? For example, dependent variable y is the travel time. We still have the travel time. And one more thing we want to discuss is the rush hour. Still, we want to see what factors contribute to the travel time. We know the gas consumption, the miles we travel, those two factors contribute to the travel time. But rush hour is also an important factor. So you travel or you're driving, well, that's around 5 in the afternoon versus you drive around 3 a.m. in the morning, the travel time will be different, totally different. So rush hour, of course, that's going to be a very important factor. But how do we model that? Because rush hour is categorical variable. You travel in rush hour or not. Only two possibilities, or only two outcomes. So that's a categorical variable. So rush hour is, so we can have a random variable. So we have a variable which is x3 in addition to the x1 and x2. So if the x3 is 0, that means an assignment did not include travel on the congested segment of the highway during the afternoon rush hour. But if the variable is equal to 1, that means the truck or the assignment included travel on the congested segment. So one more variable we have to introduce, and the variable value can be 0 or 1. So that's how we model the categorical variable with two levels. So right now we only have two levels. Travel on rush hour or not, only two levels. So that we only need one dummy variable, which is x. So let's, I think we have an Excel file. So if we open the Excel file, which is called the Butler Highway. So the Excel file is called Butler Highway. This file is uploaded on onto Blazeview. So if you have not haven't downloaded it, please do that. We are going to do this analysis. So Butler Highway. That's the file name. So if you already have this file open, we have the assignment, miles we traveled, deliveries, number of deliveries, we have travel time, and there's one more column called highway. So we have different number 0, 0, 0, 0, 1. We only have two levels, or two values, 0 and 1. 0 means the assignment does not include rush hour. If it's equal to 1, that means that assignment included the rush hour. So let's do this regression analysis. So the dependent variable is still time, travel time, and right now we have three independent variables. Rush hour or not, deliveries, and miles. Let's do this regression analysis. So let's click on data. And click on this data analysis tool.
Are you going to solve it?
The function should be there. If not, so if the function is not there, so you click the file options, add-ins. You should look for the analysis toolpath, and if you after you select the analysis toolpath, you just click this go, and you select this analysis toolpath. Click OK. Then that add-on will be there. So if you already have it, let's click this data analysis, and let's just like what we did in the video. Let's select this regression. So y data, so it's the time, so we want to predict the travel time. And the x values. So we have three variables. We need to include the miles, deliveries, and the highway. Second, third, and fourth column. We have to select all of them. Let's click questions here? So you need to have the data analysis and to do this analysis. So that's data we have. The y data, the y should be the time. How do we want to? Should include the second, third, and fourth components. So if you already have this output, we take a look at the inputs. So here, if you look at the three primary, actually we have four of them. We already have the miles and deliveries in the previous examples, but there's one more, the highway, so that's a categorical variable. And the coefficient is 0.998, and the p-value is really small. That means that variable is a significant variable. So the rush hour does impact your travel time. Okay? So that's what we have. And if we compare the two models, one is with the rush hour in our model, the other one is without the rush hour in our model. So the first one is included highway rush hour driving, and it shows the residual, and that's the histogram for the residuals. So most of the residuals are between 0 and 1. So most of the residuals, if we consider the rush hour, most of the residuals are between 0 and 1, and if we do not have the rush hour in our model, most of the residuals will be between -1 and 0. So that means in our regression model, if we include the rush hour as a independent variable, we tend to underestimate our travel time, because the residuals are most of the residuals are positive. That means the actual value is greater than the estimated value. So we tend to underestimate the travel time. But if we do not have the rush hour, we tend to overestimate the travel time. But from our sample data, from our regression model, we know the rush hour does impact the travel time. So that's how we do the categorical variable in the regression model. If the categorical variable only has two levels, 0 and 1. Rush hour, yes or no, we have to use numerical values to model that 0 and 1. So any questions on this application? So let's save the Excel file, please. So interpreting the parameters, we don't have to skip that. more complex categorical values. So the previous categorical variable only has 2 levels. What if we have 3 levels or more than 3 levels? So how do we model that? So depending on the levels, how many levels we have for the categorical variable, we have, if the categorical variable has k levels, we need to introduce k minus 1 dummy variables. So the previous case we had 2 levels, so k is equal to 2. So we introduce only one dummy variable, which is x3. But if we have k, we need to use k minus 1. For example, suppose a manufacturer of vending machines organized the sales territories for a particular state into 3 regions, A, B, C, and they believe that the regions will impact their sales. So suppose the managers believe sales region is one of the important factors in predicting the number of units sold. So it really, the region or the area really matters. Very populated area versus less populated area. You know, there's a difference when you sell things in those 2 different areas. So in this case, we have 3 regions. So if we take into account the regions, that means if we introduce 1 variable, so if we have 1 variable for the region or area, that variable has 3 levels. That means in our regression model, we need to have 2 more variables, 2 dummy variables, in order to incorporate the impact of the region on the sales. So in this case, number of dummy variables 3 minus 2, because we have 3 levels. It should be, I think it should be 3 minus 1. We should have 2 dummy variables. I think that's going to be a typo. So x1 and x2. So x1, if x1 is equal to 1, so if the sales region is B and 0, otherwise if 1 is x2 is equal to 1, if the sales region is C, 0, otherwise. So if both variables are equal to 0, that means we are talking about region 1. If x1 is equal to 1, the other one is equal to 0, we are talking about region B. And otherwise, if x1 is 0, x2 is 1, we are talking about region C. So 3 levels, we only need 2 variables. So those numbers or those combinations represent different regions. So that's how we model this application. So the model we have should be, so if we only incorporate the impact of the region on the sales, this is the model we have. The estimated sales is equal to the intercept plus those 2 dummy variables. So observation corresponding to region 1, that means both variables are equal to 0. And then after we have the model, so we don't in this application we don't have the data, but assuming we have the data and we did the regression analysis, and eventually we have the real value for those 3 parameters. So if we put in 0 and 0, that means B0 is the estimated mean sales from region 1. Assuming we already have the data, we already estimated those 3 parameters. So B0 is the estimated mean sale of region 1. And if we plug the other combinations, so we have region B and region C. So if x1 is equal to 1 and x2 is equal to 0, so that's going to mean we have B0 plus B1. So that's the mean, estimated mean of region B. And similarly, we have region C. So that's how we incorporate the categorical variable. Still, the important thing is, you need to come up with the dummy variables, or you need to formulate this basic expression. after you know how many variables or how many dummy variables you have, and you have the corresponding data, you just do what we did using the data analysis, regression, and so on and so forth. Then you will have, so Excel will tell you the B0, B1, and B2. But before that, before you use Excel, you have to make sure that you know this is the format we are looking for. So any questions on this categorical variable? How to incorporate categorical variable in the regression? So after talking about categorical variable in regression model, we are going to talk about how to model nonlinear relationship. We have been talking about the linear relationship for a while, but right now let's talk about nonlinear relationship. So we have an Excel file called Reynolds. So if we put the data in a scatter plot, this is what we have. So it shows the relationship between the month the employee has been employed versus the sales record. So we want to identify the relationship between how long an employee has been in the company and his or her sales record. So if we put, so let me show you the data. So you can also download this data here. This data file is called Reno. So we got two columns of data. So one is the month, the employee that has been employed, and the other column shows the sales record. So we don't have to draw a scatter plot because they already did that for us. So if you look at this data, do you think that's going to be a linear relationship or non-linear, or is there any categorical variable involved? So if I just look at this data without the title of modeling nonlinear relationship, I would use linear model. So let me use linear model. So let me use linear model here. So I will do, you don't have to follow me, but I will try to do a regression analysis. So Y data is scale and X data is month, label content level, and here I check residual plot. Here I have the model, the p-value. So I was just using a simple linear regression because I assume the data is linear. So the p-value, both of the p-values are really small, and I look at the residual plot. Because before I make conclusions or use this model to do prediction, I have to make sure the model is valid. So that's this is X variable versus the residuals. So this is the whole data. What do you guys think? It's valid, or do you see some problems? So the ideal case is that the residuals will be normally distributed among around 0, and the variance has to be constant for all the X variables. But in this case, I don't think we satisfy all the conditions. If we draw a line here, so it's kind of curved. So our model is not good enough. That means simple linear relationship may not work. Then how about let's try the nonlinear relationship. So before we do the regression analysis, the other thing you have to think about is, so in reality, what's going to be the real relationship between the month the employee has been employed versus their performance. So the rationale behind this nonlinear relationship is, at the beginning, the employee, the salesperson is not that experienced, but as he has more practice, the sales record has been increasing. But at some point, maybe that person thinks, okay, I'm already an expert on that. I don't have to improve my sales skills and so on and so forth, and then the sales record may go down a little bit. So it's just like our driving time versus the risk of having accident. So when we just get our driver's license, the first time we got a new car, we got a car, we start to drive, and we are really we have to be really careful, because I just learned how to drive, and when I drive, I need to check everything. So I just hold the steering wheel really tight. Okay. But after 1 year, I have been driving for 1 year, then I think, okay, I'm an expert. I don't have to be that person. I can just use one hand to drive, the other one is making phone call or just testing. When you drive, you can see a lot of drivers are like this, texting or on the phone when that person is driving. But so the risk is going to be really high. And then after that person had an accident or over time, so the risk may go down. So that person may realize, okay, that's not a good driving condition. So let's be careful. So the risk goes down here. So that's going to be a non-linear relationship. So that's the one we just had. So it's kind of, if we look at the predicted value and the residual, it's kind of curve. It's not a linear relationship. So then how to model the non-linear relationship? The first form of non-linear relationship is quadratic regression. So we know what that means is it's a constant plus b1 times one the variable plus b2 times the variable squared. So that's a general term for quadratic regression model. But still we still have one independent variable and one dependent variable. So how do we do this regression? So there are some of the forms for quadratic model, this way, depending on the values of the parameters. So we don't have to worry about those values, because after we have the Excel output, they will tell us which form do we have. So let's open the file, which is called Reno. That's the one I have. So let's open this file. So we have two columns. So month, that's the independent variable, and sales scales, that's our dependent variable. So our model format should be y hat is equal to b0 plus b1 times x1 plus b2 x1 squared. So we need three parameters, b0, b1, and b2. We should have data for x1, but how do we do x squared? So this is once that's our x data. the regression function in the Excel does not give us the capability of directly doing the nonlinear regression. But we can manipulate the data a little bit. Because here, in the regression model, we need the x data, and we need x squared. So let's treat this one, x squared, as a different variable. Say x3 or something else. And we add one more column here to represent the value of x squared. So we have x and we have squared. Let me just insert one more column. So if you right click on the B column and click on the insert, so we will have a new one. So that will be let me void and let's calculate x squared. Do that for all the values. That will be x squared. So I added one more column to show the data of x squared, so that we can still treat this one as a linear regression. But in reality, that's a nonlinear regression. If you have this equation, you just drag it down to the rest of the equation. So those two columns are input data, and this is output data. So after you have the additional column, you can just use the data analysis tool to get the regression done. Regression, y value is scale, x value is the first two columns. And we can check labels if you have selected the top row. And that's the results. If we look at the residual plots, and we still have to look at the coefficients and p-values. All the p-values are small. And if you look at the residual plots, they look better than the previous. So that means this quadratic form fits the data better. So any questions? that's a non-linear regression model. So let's save the file. So we will have the data. And the residual is much better. And one more thing is, so we said it could be a non-linear relationship or quadratic form. But next model we want to introduce is it's called piecewise linear model. So what does this mean? So if we go back to the data, it could be nonlinear, or another model we can consider is a piecewise linear model. So we have a linear line here, and probably up to here, we have another linear line, this one. So it's like this shape, linear, one linear plus the other linear. Okay? So what about that model? Can we consider that model? Yes, we can consider that model. If we go back here, so piecewise model, but still we use the Reynolds data. So that's another option we have. And piecewise linear regression model, so the model will allow us to fit the relationship using two linear regression models. So that are joined at the value of the month at which the relationship between the month invoice and sales changes. So the relationship, this is a peak point. The relationship changes at this point. So piecewise linear regression model can also be employed to fit that model. But how do we call this peak point, or the point where the linear relationship changes? It's called not. So the value of the independent variable at which the relationship between the two variables changes, or we can call it a breakpoint. So if we look at the data, we are still using the data. So if we look at the data and we see, okay, the breakpoint or the not should be somewhere around like 90 here. So this one is not or breakpoint, we have to guess. No one can tell us which value is not. So we have to guess. So it's between 80 and 100, let's say probably 90. So before 90 we use this linear model, and after 90 we use the other model. So that's what we are going to do. So how do we model this relationship? So we have to introduce a dummy variable, because we have to make sure that the model changes after the value is over the breakpoint. We are going to use another model, we have to make sure that. So we model that as variable xk, so that's going to be a dummy variable. So if the dummy variable is equal to 0, that means the value we talk about is smaller than the breakpoint. What if the value, the actual data is greater than the model of the breakpoint? The dummy variable would be equal to 1. So in this region, the dummy variable would be equal to 0. And if we are in this region, the dummy variable would be equal to 1. That's how we do it. So x1 is the independent variable that we had, and this, the breakpoint or the not, so that we say, okay, approximately it's going to be 90. And the dummy variable that we had here. And then that's the model we have. So B0 plus B1 X, so that's a simple linear model. But we have another section of the model. How to incorporate that? So we use this term. So if the value is less than the breakpoint, we have this line. So yes, so it's this line. So this term is this line. But after the value is over the breakpoint, we have to add a term so that the model is this. So that's a term. So the actual dummy variable, and if x1 is over this breakpoint, so it's going to be x1 minus the 9. If this will be a positive value, and this value, the dummy variable, will be equal to 1. Otherwise, this will be equal to 0, so we wipe off this term, and we only have this simple linear regression model. So how do we deal with this data? So the data we only had 2 columns from the original data, the month endpoint, and the other is the sale record. In order to make that regression model, the piecewise linear model, we have to add 2 more columns. One is called the variable sk, the dummy variable. So if the value, if we look at the first value is 41, because 41 is less than 90. So in this case, the dummy variable should be equal to 0. And if you look at the second one, so the second independent variable is 106, which is greater than 90. So the corresponding dummy variable is equal to 1. And then if we go back to the regression model, we have to. So in the regression model, the regression function will consider this as a variable. So we have to calculate the value or the data for this term. So x1 minus 90 times the dummy variable. So that will give us the third column. We have to insert the third column. So this. So after we have those additional columns, so we can do regression analysis. So let's do this really quick. So let's open the data file. So we have this one. I think we already used this file, so let me just copy those 2 columns to a new worksheet. Insert 1 more column and 1 here. The first one is dummy variable x. So our purpose is that if the value is less than 90, the value is 0, otherwise equal to 1. So in the Excel, let's use the if function. So it's equal to if. The first logic is if the value is less than 90, the value is equal to 0. Otherwise, it's equal to 1. So if the value, if this value, the B2 value is less than 90, the value for this cell is equal to 0. Otherwise, the value of this cell is equal to 1. So after you put this function, you can just drag it down for the rest of the record. The third one will be x minus 90 times xk. after you have those two columns, the rest of the job is to use the regression function to have your parameter. Let me show the third one. Yeah, everybody's okay with the first one. So after you have those two columns, you can do the regression analysis. So I'm not going to do this in the class. So after you have those two columns, please do the regression model and save the database. So we have one more model to cover, but we don't have time today, so we are gonna wrap up the last topic on Wednesday. So that's all we have. Today we don't have to turn in anything. So, but please save the Excel files.